SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. To recapitulate, we have been discussing about the magmatic hydrothermal deposits and essentially the hydrothermal deposits which result from felsic magmatism, which give rise to rocks of broadly granitic composition ranging from granite to monzonite, monzogranite, diorite kind of composition. So, these rocks as a whole, the hydrothermal systems that are associated with these rocks, they give rise to a spectrum of deposits, the porphyry deposits, which are distributed mostly in the convergent tectonic regimes. Now we will discuss the another class of deposits, another type of deposit rather, associated with felsic magma, but a little different type of a situation here. Here the deposits are resulting from the interaction of this felsic magma, felsic intrusive body within the crust, where there are some pre-existing sedimentary sequences, and here we broadly categorize them into something like the contact metamorphic or contact metasomatic deposits. They are mostly the dominant ones are generally the skarn deposits. In the literature, these skarn deposits have been divided into two as reaction skarns and replacement skarns, but we shall not be going by this kind of a classification. In general, these skarn deposits result when a felsic intrusive body comes in contact with the rocks through which it intrudes and is emplaced in the surrounding of the, and then here these deposits are observed to be confined to specific lithologic horizon. So, that is why you can call them as broadly as strata bound. And they are a class of deposit which are the sources, important sources of tin, tungsten mainly. They do also result iron, gold, tin, tungsten and molybdenum, gold, etc. Sometimes some rare earth mineral also. Let us first have a look on what has been the popular model for the formation of the skarn deposits or the skarn process. The skarn process could be visualized by looking at these three diagrams. The first one, which was existing in any particular domain in the crust, which has been intruded by a magma, felsic magma. Also, let me point out here, they are far more evolved compared to the kind of magma which give rise to porphyry deposits, quite enriched with many of the volatiles, for example boron, lithium and many other volatiles, including the ore forming elements. So, when this particular intrusive body is emplaced within a sequence of these rocks, then first thing it does is that it drives out the pore fluid or any of the lower temperature, even meteoric fluid or pore fluid from these sediments, and then gives rise to the skarn formation, the contact metamorphic formation, and which forms something we can call as a metamorphic aureole. In this metamorphic aureole, these argillaceous units are converted to the hornfels with typical skarn minerals as we know them, the garnet, the other minerals. This is essentially hornfels containing some ferromagnesian minerals, and then this is converted into, so in the very first, so within that, and it reacts with the and also some typical mineral like the wollastonite and diopside type of mineral, which are also which forms along the carbonate rock contact. So essentially this dotted boundary, it shows that it is converted into a metamorphic aureole, thereby creating some basically they make the condition very conducive for the fluid to be further acted upon. So in a state, and also this is a schematically it is shown as the host, the magmatic body has caught up a fragment of the sediment as a genolith here. Now in the second stage, the magma, when it crystallizes, so it eventually expels or evolves or exsolves a magmatic volatile phase, as exactly happens in the porphyry system. So this fluid is now channelized through the metamorphic aureole which was created by the initial phase of the contact phenomena to this, and then the horizons, mainly the calcareous horizons, which were converted into the skarn to the contact aureole, are acted upon by the fluid which are evolving from this crystallizing. Much of the pluton has been crystallized, much of the magmatic body is crystallized, and the fluid is evolving and escaping through, because these contact are providing the suitable channel way for the fluid to flow through the country rock. And then this zone which are shown as hatched here are basically the mineralization zone which is forming as the skarn, mineralization in the form of the tin tungsten, the oxides, or the tungstates, or the mostly the tin and tungsten form their ore minerals. So these skarns, these zones, the mineralized zones, which we can call them, which are occurring on the other side of the intrusive contact of the intrusive in the country rock, we will call them as the exoskarn. And sometimes also we do get the part of the granite intrusive itself being mineralized. So in that case we call them as the endoskarn, and this gives rise to, we can say that this coincides with the very initial phase, or the phase in which a magmatic volatile is actually playing a dominant role and causing the mineralization. The early phase mineralization is supposed to be the condition is also supposed to be manifested in them, and then now after the pluton has cooled down and the system has retrograded, it is a stage in which there will be retrograde cooling, and that retrograde cooling will allow meteoric water to infiltrate and then alter the originally formed skarns, and then the skarn minerals can get altered, the hornfels and the other part of the system. And we also do see some later stage of mineralization in the form of metal sulfides, which actually overlaps, or which are later overprinting the earlier mineralization episode, but still preserved. And so if we look at So, the source of the fluid in this kind of skarn is of course dominantly a magmatic source is always identifiable. This diagram has come from one of the most studied of the skarn deposits of the world. This has come from Dachang deposit in China, and here is the fluid inclusion data from the different parts of the deposits. So, as stated, this part is the representing the temperature even going even well above even 600 degrees centigrade or so, and the high saline, of course the salinity part is not shown, and here it is mostly done on quartz, and this is the stage A, where you have grossular garnet, vesuvianite and quartz, diopside, plagioclase, and this is the stage in which the fluid is retaining its original high temperature magmatic characteristic. And now with the evolution of this skarn system and the later on coming to the later stage, this is the stage 2, where we can call them as the, depending on the proximity, here any of the deposits which are forming, for example in the later stage away from the intrusive contact, these will be called as the exoskarns, the distal skarns, which will be having the major component of the later mineralization in the form of sulfides, and the ones which will be very close or to the intrusive contact we will be called them as the proximal skarn, and the ones which are away from the intrusive contact will be called as the distal skarn. And the stage 2 will be with the sulfide precipitation, and here the fluid inclusions have been studied from both from cassiterite as well as quartz. You could see a good degree of overlap in the temperature range studied from these two minerals. So, thus indicating or essentially establishing the coeval or the coeval nature or the same time deposition of both quartz and cassiterite at the same time. So, this is also corroborated from many other types of studies, but this gives a very good idea as to what happens in a typical skarn system as far as the fluid evolution is concerned, and parallelly with the changing pattern of mineralization for the proximal and the distal skarn. So, as far as the skarn deposits are concerned all over the world, they are categorized into different tectonic, they are observed to be occurring in different tectonic regimes. So, this is essentially is a high steep subduction oceanic type of tectonic setting, which is observed to be giving rise to iron, copper and gold, dominantly iron, copper and gold skarns. We do have a kind of subduction against the continental lithosphere. This would possibly this is moderate deep, which gives rise to tungsten, molybdenum, and sometimes in the parts as zinc and lead also. So, this possibly gives us this possibly will explain why we do sometimes have a bit of a problem in categorizing the deposits as whether it is a porphyritin or a skarn, but they can very well be distinguished on the basis of the exact morphology, the type of the intrusive and the exact mode of occurrence of the mineralization, which is strata bound in case of the skarn deposits. This represents some different other areas than the Bolivian area. This is arising mainly out of the continental type subduction. This situation, which corresponds to a transitional low angle subduction, gives rise to the molybdenum, tungsten, bismuth, zinc, fluorine kind of skarn in monzogranite, and also these are the ones which is for the porphyry molybdenum deposit, and the last one which can also be there, the skarns which are the continental rifting. In one of the diagrams also we saw the domains or the crustal domains in which during the rifting time there are emplacement of magma, magma, and essentially it is a kind of a rifting setup in which, so these magma are mostly very evolved and alkali type of magma, felsic magma, which give rise to the tin deposits, the tin skarns, and they are more richer. We could see here some of them also do have uranium, beryllium and lithium, and these are the ones which have the maximum concentration of the elements like lithium and beryllium, and these also do have sometimes development of tourmaline in the country rock because of this boron metamorphism. Okay. So, with that brief discussion about the skarn, we come to the ones which is the pegmatitic environment. Pegmatitic environment generally are the pegmatites are generally the rich source of tin, tantalum, niobium, cesium, and sometimes uranium as well as one particular example that is considered. The salient features here that they occur from near surface to as deep as 11 kilometer depths. Therefore, some kind of a classification scheme is also followed for the different type of depth range, but essentially the pegmatites, they can be told as representing the extreme situation of a felsic fluid saturated felsic magma that evolves in such a way that the last stage, the residual melt almost get changed to almost like a fluid like mass, and they get separated out of the parent crystallizing granitic pluton and they form veins. So, pegmatites are essentially seen as occurring as veins in different types of rocks, mostly the country rocks, the gneiss country rock or any kind of a country rock in which they occur as veins, and in some situations they do have been labeled as metamorphic. The only example of it being one of the pegmatite body occurring at the Rosing pegmatite in Namibia, which is also a source of uranium. So, they present the extreme case of fractionation of water rich melt from parent granitic melt, and they are rich in the volatiles, the large ion lithophile elements, the high field strength elements, and they occur as veins traversing through fractures, weak planes. They are often zoned depending on the kind of a country rock and depending on the compositional characteristics and the rate at which these pegmatites are crystallizing, they give rise to zoned pegmatites. So, essentially, since the pegmatites are essentially characterized by very coarse grained nature in them, the constituent minerals like quartz, potash feldspar and mica. So, pegmatites are actually in fact the most important and the most wide sources of industrial mineral like mica. The example is these kind of mica bearing pegmatites are available in plenty in the Bihar mica belt within the Chotanagpur gneissic complex, which we will see them in our discussion on the mineral potentials of the Indian subcontinent. And they are also rich sources of graphite, and they occur as extremely coarse grained, and sometimes these are the pegmatites which give rise to the gem variety of many of the minerals like beryl, tourmaline, which are much sought after, and they are the most the richest sources of these kind of gemstones in many parts of the world, including India. Okay. So, that with the pegmatites, we many of the others which is of uncertain affiliation, we now complete the discussion of the hydrothermal systems or the hydrothermal mineralization associated with felsic magmatism, and we will switch over to a situation which is another class of deposits where the situation is a little bit different. They are the broadly, so we will be switching over to this particular class of, but a very important class of hydrothermal deposits, which are the lode type gold deposits in many older cratonic blocks in the world, like the Abitibi province in Canada, Dharwar Craton in India, the Ilgarn block in Western Australia, Barberton mountain range in South Africa, and so on. So these are the deposits which are the lode type gold deposits in granite greenstone terrain. These are widely believed to be a metamorphogenic hydrothermal system. So we will see these deposits and see the role of metamorphism in giving rise to, or in giving rise to such kind of a hydrothermal system. So these are the deposits which are very extensively studied all across the continents, and are the rich sources of gold all over the world, including the richest gold deposit in India, which is the Kolar gold deposit, which is from where the substantial amount of gold has been produced in the country. Right at this moment also there are other occurrences where gold is being produced. So let us see these deposits. Now before you, I am presenting a model. In this model, what we see here is that there are some granitic bodies which are shown, which are basically the syn kinematic granitoid. What is shown here is high amphibolite facies metamorphism, partial melting, and absent of partial melting is absent or minor. This is essentially undergoing metamorphism without and is also associated with some granitic emplacement, the granite coming in from deeper regions, deeper sources. Now what exactly is happening here is that it is being shown that this mass of rock, they are undergoing high temperature, low pressure metamorphism, and during this metamorphic process of metamorphism there is devolatilization of this rock which is undergoing metamorphism, and there is generation of copious amount of volatiles which are essentially carbon dioxide and water, dominantly water, and charged with variable concentration of carbon dioxide in this fluid. Recall the diagram which we discussed in one of the previous classes while discussing the role of pressure, and the fluid which is being generated here are experiencing high pressure in excess of what is actually expected as lithostatic pressure here, because this fluid is somehow not being able to escape because of the low permeability of the kind of rocks which are lying above, and also that it is kind of confined by a zone of where it is acting as kind of a lid which is for which the fluid is accumulating over here. Now what is represented as these vertical structures are the ones which are the crustal scale shear zones or the faults, which are created through the process of deformation, through the process of deformation of the crust of the lithosphere. They are deep seated fracture of the shear zones, and now they become the channels through which this fluid could escape, because once these crustal scale weak zones are created, they are the zones in which the pressure is reduced, and so this fluid which is present in much high pressure will always channeled through these kind of crustal scale structures. Now if this fluid on its way up, on its upward migration, upward journey, is likely to, because this is just a cartoon that is being shown to represent the diversity in the host rock type for the occurrence of these gold deposits as observed in many different parts of the continents. For example, here we have a mafic body which is a unmineralized iron rich tholite, and this fluid could possibly maybe passing through such kind of a rock horizon. This horizon is a chemogenic sediment which is a banded iron formation. The fluid could also encounter a horizon like this, There could be some carbonaceous sediments which will be having a environment which will be reducing, and also the fluid might get ponded within that kind of a horizon here. Other than the fact that these, as discussed before, these crustal skull shear zone themselves will be the locales of deposition of this huge amount of silica that is dissolved in this fluid, which is generated as a very high pressure temperature conditions, and will be present as what we call as mega veins or lodes. And the way we see them in different parts, that they constitute. So, what we observe basically. So, coming to the situation as to how what kind of lithology and what kind of mode of occurrence we see for these gold deposits. So, number one is that they might occur as lodes. Lodes means whatever is present in a shear zone which could be running for several kilometers in its several tens of meters, hundreds of meters or even kilometer in its strike length, and is of substantial crustal depth extension, and will be characterized by complicated intense deformation signatures of deformation, shearing mostly. They are shear zones, and we see them that they are present as gold quartz lodes. So, here we get free gold deposited along with the quartz, we get them as gold quartz lode. The other possibility, number 2, we get them as lodes with quartz gold, also sometimes some amount of sulfide minerals like pyrite, arsenopyrite also associated with them. We get them as within the banded iron formation. I will just discuss about the where from this banded iron formation could have come, that this with replacing the iron oxide phases in the banded iron formation and formation of the sulfides, and these sulfides being the host for the gold which is liberated within this from the fluid which traverses through this and encounters the banded iron formation. This mafic body may also act as a trap. So, the gold could also be present as deposited within this deformed mafic body. The gold could also be present in the carbonaceous sediment. So, the situation is that this particular fluid which is liberated from the dehydration metamorphism of this rock is also charged with is basically is enriched with the precious metal in substantial amount, and is transporting the gold, as we just discussed, that this kind of gold where substantial amount of carbon dioxide is dissolved might have acted or might have enhanced the gold solubility and would have transported the gold in this fluid. We will continue discussing on this very important class of deposit, which are the lode type gold deposits in greenstone terrains in across the continents, and very popularly being now known as orogenic gold, and we will continue discussing this, continue discussing the next class. Thank you.